The purpose of this video is to teach what matrices are and how to use them for 3D game and graphics programming. Before you get overwhelmed, don't. Basically, I put this slide together and I repeat it at the end of this video to show that basically everything that you need to know about matrices for 3D game programming and graphics programming fits on basically just one slide. If you know everything on here, you pretty much have mastered matrices for game programming. And matrices seem pretty overwhelming at first, but it's really not that complicated once you start getting it. Matrices are probably a little tough if all this is brand new. However, the API or framework you're programming your game in will do all of the math for you, including the matrix algebra. It's good to know how the math works, but don't get too bogged down in learning the math. You don't need to learn how to do long division in order to divide two numbers using a calculator. You merely need to know why you're dividing the two numbers and what the answer means. And using matrices in game programming, since the API does all the math for you, it's pretty much just like using a calculator. Here's all you need to know about matrices. Matrices hold a position, orientation, and 3 scale factors simultaneously. So matrices are primarily just a way of describing where an object is in the 3D game world and what direction it faces. Or maybe I should say world matrices are that. The projection matrix is a little bit different, but we'll cover that. You should have one or more matrices for every object in your game world. You should attempt to only store the position, orientation, and scale in the object's world matrix. The next video I'll do is actually on gimbal lock, and I'll explain that better in the gimbal lock video. You combine the information inside of matrices by multiplying them together. You would think that combining two matrices would be addition, not multiplication, but it is multiplication, and we covered that a little bit here later in the video. In fact, really, we're going to cover all this in this video. Just want to give you a high-level overview starting out. You empty a matrix by making it an identity matrix. The order you multiply matrices in will give you completely different results. The order you multiply them in matters. This is mostly due to the fact that all rotations must always occur at the origin. Anytime you rotate any object in the 3D world, you have to move it to the origin, rotate it, and then move it back. The very first thing a shader does when it goes to draw a model is combine the object's world matrix with the view matrix and the projection matrix. This tells it where the model should be drawn on the 2D screen. Every position of every vertex is multiplied by this WVP world view projection matrix to determine where it draws on the 2D screen. So really it's the projection matrix that projects the 3D world onto a 2D screen. The world and view matrix are a little bit different, but they're combined with that to make one matrix where everything gets drawn to the 2D screen. We'll cover that more as we go. To uncombine, think subtract, one matrix from another, you multiply by a matrix's, is that matrix, how do you say that? A matrix's inverse. You would think that just like addition, or to combine, you would think would be addition, and it turns out it's multiplication. And to subtract, you would think it would be subtraction or maybe even division, but it's not. It's multiplying by an inverse matrix, which is sort of similar to the division. The view matrix is by definition an inverted world matrix. Projection matrices are totally different than world matrices. Every object has a world matrix to place it properly in the 3D world. The position of the camera is the view matrix. The projection matrix contains all the math necessary to convert 3D positions in your 3D world into 2D positions that can be drawn on a 2D computer monitor. We always use either 4x4 matrices or 4x1 matrices in 3D game programming. that's basically everything you need to know. And at this point, since I haven't explained any of this, even that may sound a little bit overwhelming. But basically, if you understand all the things that I just said, you basically have mastered matrices for game programming. History. The book, The 9 Chapters on the Mathematical Art, which was written before the 2nd century BC, is a composition of many centuries of Chinese scholars. It describes the use of arrays to solve mathematical problems. In 1659, Jan de Witt represented transformations using arrays in his book Elements of Curves. So this has been around a lot longer than computers or computer graphics have been around. This matrices is really a mathematical thing that goes back, centuries into, ancient Chinese writings, and it didn't start with computers. There's a type of mathematics or mathematics class called linear algebra, where vectors and matrices are primarily taught, although sometimes you'll be introduced to matrices in earlier classes. What matrices are? Think of them as black boxes that you load math formulas into, where all these formulas get combined and have their results stored in the matrix, which can then be applied to an object to position, orient, and scale it, or to operate a camera. A way of doing math using the cells of a box, much like a spreadsheet. So if you look at a matrix internally, it looks like a box of cells, or kind of like a spreadsheet. But for the most part, you want to think of matrices as just these black boxes that you load math into, and then apply the end result to position, orient, and scale an object. What matrices are not? A movie starring Keanu Reeves. Yeah, okay, it was not a very funny joke. What is a matrix? Matrices are just boxes with rows and columns of numbers, or possibly mathematical functions that evaluate numbers. Over on the right-hand side, I have an example of a, 3x2 or 2x3 matrix. Basically, it can go horizontally or it can go vertically. It can go vertically. And so it's either 3x2 or 2x3, depending on whether the horizontal is first or the vertical is first. They can have any number of columns and rows. However, for 3D game programming, we pretty much exclusively use a 4x4 matrix. We pretty much use 4x4 matrices, unless you want to look at 3D vectors as a 1x4 matrix or matrices. Obviously, the singular is matrix and the plural is matrices. There are a special set of mathematical rules about how to use matrices together called matrix algebra, which is mostly studied in a linear algebra course. All matrices are arrays, but not all arrays are matrices. So you'll notice in the example on the right, I have not only integers and real numbers with decimal places, but I also have functions like sine and cosine. So the matrix can hold more than just numbers, and we'll look at that a little bit more, which is part of the reason I say matrices, think of them as a black box that you just load up formulas in, and then apply the results. I'm using kind of a matrix notation with brackets to kind of show that it's a matrix. What is a 3D game programming matrix? The matrices we use for game programming are almost always 4x4 with 4 rows and 4 columns. Matrices with an equal number of rows and columns are called square matrices. A matrix with a diagonal line of ones is what is known as an identity matrix. It is considered to be empty. So on the right hand side, we have an example of a 4 by 4 identity matrix with 4 rows and 4 columns. And you'll notice the diagonal line of ones going from the left to the right. This is considered an empty matrix. Multiplying the identity matrix times any other matrix will, much like multiplying by 1, give you the same matrix. Multiplying by a zeroed matrix will destroy the matrix completely and result in a zeroed matrix. You would lose all the information in the original matrix. Of course, we have to get into matrix multiplication for you to actually see that, but just know that this is kind of like a matrix with 1, and since we're multiplying to combine, you're basically taking one matrix and multiplying it by 1, which gives the exact same matrix, just like anything else you multiply by 1. Whereas if you were to multiply by 0, it would basically zero out the other matrix, and the answer would be 0, and you would lose the other matrix. Matrix addition. No one ever does this. It's basically like laying the two matrices on top of one another and adding them together. You can also think of it like adding cells in two spreadsheets to produce a third spreadsheet. Both must have the same number of rows and columns. So that's a rule of matrix algebra, that they have to have the same number of rows and columns. So you can see if the example at the bottom, we basically have two matrices. We're going to add them together, and it's just kind of like you lay one on top of the other, add the numbers in the same cells together, and store that in the same cell for the results. If you kind of look at it, you can see that 4 plus 1.7 is 5.7, 0 plus 0 is 0, 0 plus 4.2 is 4.2, and then down in the next row, 0 plus 0 is 0, 1 plus 1 is 2, 5 plus 0 is 5, and so on and so forth. And you can see that we're just adding each individual number together, but we don't use this in game programming, so for us this basically doesn't matter. Matrix subtraction, basically the same thing, except for you subtract instead of add. And again, no one ever does this in game programming, so it doesn't really matter for us. I'm just kind of showing you that there's a whole mathematics around this matrix thing, most of which we don't care about. Matrix multiplication by scalars. Again, we don't really do this in game programming, but this is how you do it. A scalar, as I explained in the vector video, which I hope you watched, is basically just a normal number. A scalar is just plain old regular number, and you can multiply a number by a matrix. And the way you do that is you take that number and you multiply it by every value in the matrix and store it in the same place for the result. So 2 times 1.7 is 3.4, 2 times 0 is 0, 2 times 4.2 is 8.4, and so on and so forth. Matrix vector multiplication. Now we do this. You'll do this if you write shaders. This is basically multiplying a matrix times a 3D vector that has been put inside a 4D vector. The single column matrix is the equivalent of the vector 6.2, 4, 3 in the example below. The fourth value is w, or xyzw. When it is a 0, the column is a vector, and when it is 1, the column is a point. Or to say that another way, when it is 0, it represents a direction, and when it is a 1, it represents a position in 3D space. More specifically, the w equals 0 values are directions of the local x, y, and z axes, and the w equals 1 value is the position in 3D space that this matrix holds. We'll look at that in a lot more detail later. There's an example at the bottom of how to multiply a vector times a matrix. And so we've taken our vector 6.2, 4, 3 and put it into this 4D vector as a 4 by 1 matrix and multiply it by 4 times 4 matrix. This is what we're doing with our matrices. When we use a matrix to describe how an object is placed in the 3D world, where it's placed, and so forth, at the end, the shader graphics card is going to multiply our matrix, our worldview projection matrix, times the position in our mesh, our model's vertex. Each vertex in the model will get multiplied by the worldview projection matrix. So we take that position in 3D space, and the position is actually the position where the vertex was positioned in the modeling program, and the world matrix describes where it's actually placed in the 3D world. And so when you combine them, it will give a position as the result here that describes where that position is on the 2D screen once the object is projected onto the 2D screen. So we're getting a little ahead of ourselves, but this shows an example of how you would do this math, the matrix times a vector. And with multiplication, you have to you can't, the matrices don't have to be exactly square. They don't have to be exactly the same. There's a specific rule, and I think it's basically because we're doing a 4x4 matrix here. We could do a 4x1 matrix to multiply it against, but we could not multiply it with a 3x1 matrix, for example. That's all in the laws of matrix algebra, and really not something we need to know here. But you should pay attention to the fact that in order to multiply the matrix times a vector, we're actually taking the dot product of the vector here with each row in the matrix. Every row is getting dot product to the position vector, and then we go through the math of doing the dot product, and the final result is a 4x1 matrix, another vector, which holds the resulting position. What is a 3D game programming matrix? Okay, so here I've tried to kind of draw out a matrix so that you can kind of position and or look at how it's how to think about it. So on the left hand side, I have the 3D Cartesian coordinate system, the x, y, and z axes, and then coming out of that, we've got this red arrow that represents a position or an offset from the origin. And then we have this box of basically three vectors that mimic the x, y, and z axes. Notice that basically the y's are in black, the z's are in green, and the x's are in blue. And so you can kind of imagine that at one point this cube was lined up with the axes over there on the Cartesian coordinate plane in 3D space, and at this point it has been rotated so that it faces a different direction, and it's been offset so that it's positioned away from the origin. So down at the bottom, I have a 4x4 matrix, and this is basically what gets stored inside of a matrix, what the cell values, if you will, within the matrix actually represent. And you'll notice that the first column is basically an x-axis, the second column y-axis, the third column z-axis, and the fourth column position. So said earlier that basically if that w value, the fourth value, is 0, then it's a direction or a vector. And if it's a 1, then it's a position. And you can see that down in the last row there. Now, also notice going horizontally, the entire first row has sub x as a subscript. So it's x-axis x, y-axis x, z-axis x, and position x. And then y across the second, and z across the third, and w for the fourth row. So basically you have inside this matrix 3 vectors that are, by definition, they have to be mutually perpendicular, and they describe this orientation. They basically form another set of axes. Like you have your original x, y, and z axes, and then this, if it were aligned with that, would have a second redundant x, y, z set of axes that it describes. And by rotating them, we can talk about a rotation away from the original axis. So it's a way of describing how something has been rotated using these 3 vectors. We always keep them mutually perpendicular, so they're all 90 degrees away from one another at all times. But by rotating them together, they describe like another axis and how it has been rotated differently than the original axis. And then that doesn't really allow us to position that in 3D space. So the fourth column basically is an offset, which stores the position. And then we also mentioned scale. I don't want to get into scale too much because I really say that your scale should always be 1 and you shouldn't really use scale. But the diagonal across here, which has a bit of a shadow to it, is your scale. And we talked about the identity matrix has 1s across there, so everything has a scale of 1, which is basically an empty scale. And then it works out kind of handy that if you think of that x-axis there, the x, y, and z of that would be, again, on the identity matrix, 1, 0, 0, 0. So if you think of x being 1 and y and z being 0, then it points straight down the x-axis when it's an identity matrix. Likewise, the y-axis would be 0, 1, 0, 0, so that the y-axis would be pointing 1 unit along the y-axis with everything else zeroed. So that would be basically just pointing straight down the y-axis. And then the z-axis in an identity matrix would be 0, 0, 1, 0, which would be pointing straight down the z-axis. And the position would be 0, 0, 0, 1, which would be no offset. So it would be positioned at the origin and perfectly aligned with all 3 axes. And then as you change it, it's basically its own private axis system that you're rotating and positioning to describe a different orientation or a different position. And usually it'll be describing the orientation and the position of your object. Types of matrices. We basically just went over the identity matrix, where you have 1s in the diagonal from the top left to the bottom right, where you have, looking at the bottom, you have the x-axis, the y-axis, and the z-axis represented as 3D vectors. And the x value on the x-axis is the only one set to 1. The y value on the y-axis is the only one set to 1, and the z value on the z-axis is the only one set to 1. I don't know if I made it clear earlier, but if you look at these 3 3D vectors as mutually perpendicular axes, you obviously have three components for the vector: the x component, the y component, and the z component. And you can see the x components in the first row, the y components in the second row, and the z components in the third row. Of course, the fourth row is your 0 or 1 to determine whether it's a vector or whether it's a position or point. A couple of the other types of matrices that you'll see commonly are a scale matrix, which we've already somewhat covered. Again, this is the diagonal here, where we have the s's, or in the bottom where the diagonal is in shadow. Basically, if those values increase, the scale of the model, the size of the model along the x-axis, the y-axis, or the z-axis will increase or decrease. 1 being the standard size. Anything smaller than 1 will decrease size. Anything larger than 1 will increase size. And you can scale differently on the x-axis than you scale on the y-axis, than you scale on the z-axis. If you use scale, you should almost always scale uniformly, so that your scale is scaled by the same amount on all three axes. Really, I would advise not using scale at all. Optimally, you would set the scale correctly in the modeling software, whether that's Maya, 3D Studio Max, Blender, whatever you're using. The artist should create the scale of the model correct in the first place, and you shouldn't have to use this, but it's there if you need it. Even if you do use it, you probably want to scale uniformly most of the time. Translation is about movement. Here you see the T's match up with the positions in our matrix down at the bottom. Basically, when you multiply the world matrix times the translation matrix, that's going to combine the position of the two. And so it's, even though you're doing multiplication, it's basically adding the original position to the translation position, and that'll be stored in your result matrix. But it's basically just an identity matrix with a position in it. And then finally, we have the rotation matrices. We talked in the vector video how there is basically no such thing as a 3D rotation formula, and we covered the rotation formula, and you should see that here on the right hand side. That should look pretty familiar to you. But we basically we basically use the 2D rotation formula and then rearrange it so that it works on all three axes. The z-axis rotation basically shows the original rotation formula where you're rotating around the z-axis and on the xy plane. And you can see there final x equals the cosine of the angle times the original x minus the sine of the angle times the original y, and the cosine of the angle of rotation times the original y plus the sine of the rotation angle times the original x will give you the new y value. And then if you look at the matrix that matches up with that, you'll see basically the same thing. You'll see how we've taken that rotation formula, that 2D rotation formula, and put it into the matrix. So we have in the top row, we've got cosine theta, or the cosine of the angle, and the negative sine of the angle, which you see that in the final x formula, and the cosine of the rotation angle that would be multiplied by the original x is actually getting multiplied by the x-axis here, and the negative sine of the rotation angle is getting multiplied by the y-axis. And the same for the final y value, although it's kind of switched around backwards, but since it's addition, it's not going to matter. The important thing is that for the final y value, the cosine of the angle is matching up with the y-axis, and the positive sign of the rotation angle is getting matched up with the x-axis. And so it should be fairly clear here that this is the original algebra rotation formula that we had with vectors. It's the exact same formula. We're just plugging it into a matrix. And then when we take this rotation matrix and we combine it with a position, an x and y position, we're going to wind up with basically the same results. We're doing the rotation formula the same way, and the math all works the same way, except for now we're using matrices to do the rotation formula. But because there's only a 2D rotation formula, there's no such thing as a 3D rotation formula, we take the fact that it rotates around, basically we take the fact that we're doing a 2D rotation on the XY plane around the z-axis, and we just switch out the axis. For the y-axis rotation, we do the rotation on the xz plane, and for the x-axis rotation, we do the rotation on the yz plane. Same formula, we're just switching it around so that we change which axis we're rotating around and which plane we're doing the rotation on. If you haven't watched the vector video, I went over this in quite a bit of detail in the vector video, and you might check that out if this doesn't make sense. Matrix multiplication. This is what we're doing all the time in game programming. Basically, you're just combining the two matrices. You take two matrices and you combine them. If you've got a world matrix that stores an object's position and orientation, and you want to change it to a new position, you'll multiply that times a translation matrix to translate it to a new position. Or you'll multiply it times a rotational matrix to rotate its orientation to a new orientation. And you're combining them, which you would think would be addition, but it's actually multiplication. And when you see the results at the bottom, you'll see, oh yeah, it did combine them. It works out. When you multiply them, they end up being combined. Whereas with addition, it would not combine them. And you'll also notice that we're basically taking columns and doing a dot product with the row of the opposite matrix. But all the math is using dot products, and then you calculate the dot product values. And with all of this math, I'm just kind of briefly showing you, introducing you to how it's done, not really digging deep into the math itself. We covered the dot product in the vector video, and you can watch that to kind of see how a dot product is done. But basically this just kind of gives the overview of what it's doing and kind of quickly walks through the results and shows how it's done. If you really want to get into exactly how this is done, again, you don't need to, because pretty much any framework or API that you have will do this math for you. But you can study linear algebra, find a matrix algebra book, and it'll explain in better detail exactly how all this works. But the important thing is to understand that you take two matrices and you combine them by multiplication, not addition, and the end result matrix will be the two matrices combined. And you can kind of see it if you just kind of look at what we start with and what we end up with, and know that, you know, the first three columns are the three vectors that represent the three axes of the local axis, and the fourth column is the offset or position represented. And you can see in the first matrix the position is 5 0 0. Second matrix it's 0 0 0. So we're basically adding 0 0 0 to 5 0 0, and in the results down at the bottom the position is still 5 0 0 because you added nothing to it. And then we see the scale along the diagonal, which starts out as a scale of 3 on all 3 axes, and we multiply that with a scale of 4 1 1. The ones aren't going to change, but scaling something that was already 3 times normal size to 4 times normal size of that on the x-axis is going to give you 12 times the normal size. But the other 2 axes where it was 3 times the normal size, that's scaled by a factor of 1, so it's still 3 times the normal size. Let's see what else we can see. But you also see that the scale actually winds up being applied not just to that value. Like in the second matrix, you've got x, y, z. The z-axis is 0, 5, 1. Okay, so in the first matrix, the z-axis is 0, 0, 3. Second matrix, it's 0, 5, 1. You're combining those. So that's a vector pointing down the z-axis. And then the result becomes 0, 15, 3. So we already kind of covered why the 3 is 3. But the 5 is scaled by a factor of 3 too, or 3 also. The 5 is scaled by a factor of 3 also, so it becomes 15. When you do a lot of operations on it, it starts becoming less clear, but the scale factor ends up being scaled along the entire vector, not just that one value. Like all 3 values of the vector will actually end up being scaled, and you can see that in the 15 there. But basically the thing to know there is just that you don't add matrices together to combine them, you multiply the matrices together to combine them, and then you store the results as the new matrix. And also remember that the order that you multiply them in matters, because the end result will change depending on what order you multiply them in. Orthographic projection matrices. So your projection matrices are going to take your 3D world and project it onto a 2D surface so that it can be drawn on a 2D computer screen. You have this imaginary 3D mathematical world, and you just want to basically flatten that out onto a 2D surface so that you can draw it. And for the orthographic projection, you could basically just take away the z value and just make it x, y, and just throw away the z value so that it becomes 2D. But there wouldn't be any depth for layering at that point. And the other problem with that is that horizontally and vertically, you're not really limiting your world. Your world is almost infinite in size, and the camera can only capture so much on the screen. So we have the box on the right side, where we have the near plane in yellow and the far plane in red. That's like the front of the box and the back of the box. And then we have the left and right side of the box and the top and the bottom of the box. And basically everything within that box is going to be projected basically on the near plane and become 2D. And this is kind of a brief look at the math inside of an orthographic projection matrix. It's basically it's basically taking this 3D world that's only the part that's in our box here, and flattening it out to be 2D so that it can draw it on a 2D computer screen. And this largely shows the math for that. I'm just kind of briefly showing it as an example rather than going into detail about how the math is actually done. But we basically have the right side of the box minus the left side of the box positionally, the top minus the bottom, the far plane minus the near plane, the near over the near minus the far plane. And if you go through the math correctly, it should basically compress it all down to a 2D plane so that it can be drawn on a 2D screen. But the problem with this is it doesn't have perspective. No matter how far something away or how far away something is, it's going to look like it's all at the same distance. And so to make it appear as it that it has perspective, use a perspective projection matrix. And instead of a box there, that's going to look more like a 3D pyramid with the top cut off. And my artwork here is not that great. I'm trying to draw a 3D representation here and didn't do a very good job. But you still have basically the yellow near plane and the red far plane. The red far plane is obviously a lot bigger. And then you have the left side of the pyramid, the right side of the pyramid, the top of the pyramid, and the bottom of the pyramid. Basically, it's a four-sided pyramid with the top kind of cut off here. And everything inside of the four-sided pyramid there is what is going to be projected onto basically the 2D near plane. And using this formula, basically things that are closer are going to appear bigger. The further away they are, the smaller they're going to appear, and the closer they are, the more they're going to move to the center, and the further away they are, the more they're going to move out to the edges. And that will draw things in perspective so that they actually appear to be 3D, and we'll get a 2D drawing that looks 3D using the perspective projection matrices. And then over in the left side here, we kind of show the math of how that's done. But basically, you really don't have to know much about these projection matrices. You need to know that the orthographic projection matrix is basically used for 2D when you want things to look 2D and flat, and the perspective projection matrix needs to be used when you want to do 3D. And you'll need to know how to supply the correct parameters to that when you create your projection matrix. But for the most part, you just create your projection matrix at the beginning. And you'll have to give it like the angle for the field of view, which is generally going to be about 50 degrees, and the aspect ratio of the screen. I think there's another parameter that you have to supply, but you just set that up once at the beginning of your program, and you don't change it. You just leave it, and that's going to project your 3D mathematical world onto the 2D computer screen. So the projection matrix is very different than the world and the view matrix. The view matrix, the world matrix basically describes the position, orientation, and scale of an object in your 3D world. The view matrix basically describes the position and orientation of your camera, not so much scale. But basically it's the same thing as a world matrix, except for it's for the camera, and it's an inverse because you're doing everything backwards. The projection matrix is completely different, and this is getting back into the idea of matrices as black boxes that you load up formulas in. We're just loading up all these formulas into this projection matrix, and the formulas convert the 3D world into 2D. One set of formulas does it orthographic, so that it's flat in 2D, and then the other set of formulas does it in perspective so that it appears 3D even though it's drawn on a 2D surface. But basically, when it goes to the graphics card to draw the object, it's going to take the vertices for the object, which will describe the object itself as it was drawn in the modeling program, Max, Maya, Blender, whatever, and then you'll take the object's world matrix to describe how it's positioned into the scene, and then multiply that times the view matrix, which will simulate the position and orientation of the camera, and multiply that times the perspective or the projection matrix, whether it's perspective or orthographic, and you combine those three matrices into one matrix, and then it contains all of the math necessary to position it in the world, position the camera, and project it to the 2D screen in one matrix. And so mathematically it's extremely efficient to take that one matrix with all that combined information in it and apply it to every vertex in your object, so that the graphics card knows exactly on the 2D screen where that vertex is, and it can draw the object because it knows on the 2D screen where the vertex is. So the view matrix is an inverse matrix. An inverted matrix is one that can be multiplied by itself to give an identity matrix. Basically, it reverses a matrix. If combining matrices through multiplication can be thought of as addition, then uncombining matrices through multiplying an inverse matrix can be thought of as subtraction. At the top, I basically have the definition of an inverse matrix. You have a matrix. If you multiply it times an inverse matrix of itself, you'll get an identity matrix, or an empty matrix. Down at the bottom, I have the idea that if you combine two matrices by multiplying them together, A times B, you'll get the result matrix C. If you want to do the opposite and basically subtract, you take the result C and multiply it times the inverse matrix of B, and you'll get the A matrix as the answer. The view matrix. The view matrix can be thought of as a world matrix for our camera in our 3D world. It stores the position and orientation of our camera. However, it's inverted compared to a standard world matrix because everything must be backwards for it to work correctly. There's no real camera in our game world. Basically all we had was the projection matrix, which basically takes whatever is in front of the camera in that box or in that pyramid and projects it onto a 2D plane. But there's really no way to take that box or pyramid and get it away from the axis. You could put it on a different axis. I mean, it's the way it works, it's looking straight down the z-axis. You could look down the negative z-axis, you could look down the x-axis, you could look down the y-axis, but the problem is that you can't get away from an axis. You can't look at an angle, and once it's looking down that axis, it's stuck looking down that axis, and there's really no way you can change that. So the way that we simulate moving a camera through the scene is by moving the entire scene in the opposite way that you would imagine the camera moving. If you look at the picture of the monkey here, on the left we've got a picture of a monkey, and then on the right we have a picture of the monkey where the camera has moved to the right. Or is that really what happened? Maybe the monkey moved to the left. Did the monkey move to the left, or did the camera move to the right? Well, there's really no way to know from these pictures. If there were more objects in the scene, you might be able to tell which it was. But here you have no idea. In the way the view matrix works is when you want to make it look as if the camera moved to the right, you move everything in the scene by the exact same amount to the left in the opposite direction that you wanted to move the camera, because again, the camera can't move. So if you move everything in the scene by that amount, it will appear as if the camera moved. So if you rotate everything in the world 10 degrees to the right, it will appear as if the camera rotated 10 degrees to the left. Everything is in reverse. You're moving the entire world, either rotating it or repositioning it to make it appear as if the camera rotated or the camera was repositioned, but the camera can't move. So the job of the view matrix is to move the entire world, the entire game world, by a uniform amount to make it appear as if the camera moved through the scene. But it's important to understand that everything is backwards, and that's why it is an inverse matrix. The look-at method. Pretty much every game programming framework has a look-at method. This is generally the way you build a view matrix, but it can be used for other things. It generally takes 3 parameters: position, position to look at, and up. It works by defining a vector from the position to the position being looked at. It then uses the up vector to form a 2D plane that can be used for a vector cross product to form 3 perpendicular axes like in a world matrix that define the orientation. The position can be used to define the position of the camera directly. It will likely build an inverted matrix compared to a standard world matrix so that it can be fed directly as a view matrix without inverting it. To turn it back into a world matrix, invert it once again. So basically it's a world matrix, but the way the look at method works, it takes these 3 parameters: position, position to look at, and up. And it's real confusing what up is. So the way it works is it forms a vector between the position and the position to look at. That gives it the direction to look at and the distance between the position and the position to look at. Then it takes the up vector and basically puts their tails together. The up vector is supposed to be the area above the camera. So it's up relative to the camera, not up relative to the world. And then you have 2 vectors with their tails together, and you can imagine them living on the same 2D plane. So you have a 2D plane at that point, and you can use the vector cross product of those 2 vectors to find a mutually perpendicular vector that points directly out of that plane. And theoretically at that point you have mutually perpendicular x, y, and z or z axes that basically form your world matrix. There's a cheat that you'll see used a lot where they'll just put the up direction in up. So if y is up, then it becomes x equals 0, y equals 1, and z equals 0. And that actually works a lot of times. If you go through the math, when you pitch the position to look at vector up or down, the up vector theoretically should pitch up and down with it, but if you continue to point up, it won't be perpendicular. Those 2 vectors won't be perpendicular. They won't be 90 degrees apart, but they still will live on the same plane. So when you do the vector cross product, you'll still get a vector that points out of that plane, and it ends up basically working. The problem is that when you flip it over, when you're like doing a flight simulator or something where the camera actually does turn upside down, and you're feeding it an up vector that is not above the camera but is actually straight up, your code will have a bug in it. It'll freak out. So just feeding it an up value is a cheat that often works, especially if you're like just walking around the scene and you're not doing a flight simulator where you turn upside down or something. That tends to work, but if you don't do it correctly, it may end up biting you eventually. And the correct value is a vector that points directly above the camera, no matter how the camera is oriented. And that's basically it. We're back to our original slide that contains everything you need to know about matrices for game programming. And we've pretty much covered it all at this point. And hopefully you've got a pretty good idea of what all this means. But that's basically everything you need to know in order to do 3D game programming.